Thank you for this great opportunity of sharing the latest progresses in the deep reconstruction area. In this presentation, my postdoctoral fellow Weiwen Wu and I will focus on deep CT reconstruction. Our results are based on long-term close collaboration with all these co-authors and others. We have 4 parts to present. The first part is on stabilized tomographic reconstruction. The second is on weakly supervised multi-source stationary micro-CT reconstruction. The third one is on photon counting CT, and the last one is explorative, and we talk about field view and limited angle problems. I guess many of you saw the left cartoon before. It suggests that rebranding classic statics as either machine learning or AI results in significantly more attention and traction. This joke has some valid point, but could be misleading since deep learning and classic statistics are quite different despite their similarities. I think the middle cartoon has more point. Computer scientists and statisticians work together, and their knowledge and skills are gradually fused to advance the field called data science. In some sense, the fusion of statistics and computer science is a good analogy of the integration of classic reconstruction algorithms and deep reconstruction networks. Our recently developed stabilized reconstruction scheme is a good example of such integration.
Many thanks for Professor Wang's introduction. At first, I will introduce how to stabilize deep image reconstruction neural networks. As we all know, the history of image reconstruction can be classified into 4 stages. The first stage we call it analytic reconstruction. However, its results usually contain high-frequency artifacts. Regarding at the statistical reconstruction method, a reconstructed image is strongly influenced by the penalty term. To overcome this challenge, compressed system-based iterative reconstruction method were developed. However, not all the ground truth in practice is sparse. Since 2016 years, deep learning-based reconstruction methods have attracted much attention and rarely achieved great performance. However, there are concerns on the black box nature of the deep reconstruction. Typically, there are 3 hands of instabilities were recently reported in the PNAS paper. In this paper, the authors described the 3 instabilities very carefully. Type 1 instabilities, called the false positive, that means a deep neural network, including the AutoMap published in the Nature, is subjected to the adversarial attack. Type 2 instabilities is the false negative, that means the small features missing in the deep neural network reconstructed images. The type 3 instabilities, we call it as overload, which means more data set decrease the reconstruction performance. For example, the FBB component is trained on 50 views dataset. The performance will be decreased with 100 view dataset. To stabilize the deep neural network, actually, we have gave a general answer in one of the IEXC's review in 2016 years. Again, our general idea is to incorporate deep reconstruction networks into the classic iteration framework as well as the compressed system. In this way, the overall reconstruction method will incorporate both deep prior and compressed ceasing prior to satisfy the requirement of the data consistency. Specifically, here we developed one of analytic, compressive, iterative deep. We call it asset network to address this problem. We first use the deep reconstruction network to reconstruct the initial imager. Then, the initial imager passing through the compressed ceasing to promote the sparsity and obtain the filtered imager. Next, comparing the original data and the data from the filtered imager to generate raster data, so that to achieve imager increment. After several iterations, we can obtain high-quality reconstructed imager. If you are interested in this our work, the detailed mathematical convergence proof can be found in the fifth version of our Hive paper. And this is the reconstruction result of our acid against the type 1 instabilities in the CT case. For the reconstruction results, one can see that our acid can obtain better image quality than that obtained by the CS against type 1 instabilities. The quantitative result show that our acid can obtain better results than CS methods. This is the reconstruction result of our acid against the type 1 instabilities in the MRI image reconstruction. For the MRI image reconstruction, we can obtain that our acid can obtain better image quality than that obtained by the CS. The quantitative results also shows the acid can obtain better results than CS methods. This is the reconstruction results of our acid against the type 2 instabilities in the CT case. From this picture, we can see that our acid can accurately recover the small structures in the CT case. The quantitative, in terms of the SSIM and PSNI, further confirms the advantages of our acid. And this is the reconstruction results of our acid against the type 2 instabilities in MRI case. For the reconstruction results, one can see that our acid can obtain better image quality than that obtained by the CS against type 2 instabilities. The quantitative results show that our acid can obtain better results than CS methods. From this picture, one can find our acid can also increase the reconstruction performance with more import data, since the quantitative result can be better with more import data. At the second part, I will introduce our weakly supervised deep reconstruction network. To reach the higher temporal resolution for heartache CT imaging, the multiple source detect Paris-based CT imaging system were proposed more than 20 years ago. However, most of these multiple source detector systems are only in theory. Now, fortunately, we first designed and implemented the multiple source detector system for heartache CT imaging. This system contains 29 X-ray source detector pairs. However, such system can only cover the part of the object, resulting in interior CT reconstruction, as well as the sparse view reconstruction. So, hard to obtain higher quality imagery from 20-line projections for an interior reconstruction is a big challenge. Here, we further designed a deep reconstruction method, which incorporating deep priors into traditional tensor prior. The tensor dictionary is trained by deep network refinement results. Furthermore, the deep refinement results are considered as the prior imager. We further proposed a iteration tensor dictionary learning-based optimization deep reconstruction method, named as the TED. This is the heartache dynamic reconstruction results from our smart system, as well as our proposed TED reconstruction algorithm. From the left hand, we can observe that our test can obtain better image quality with much more image features and clear image edges. From the right hand two images, they demonstrate that our proposed test can accurately reconstruct clear and accurate blood vessels with higher temporal resolution. In this section, I would like to share our deep reconstruction work in the aspect of photon-counting CT imaging. The photon-counting imaging is well-known the next generation of the CT. However, how to obtain good image quality from the noise projections is a big challenging problem. To solve this problem, we proposed the unit with LP-low, TV, residual learning, and anisotropic adaptation. We call it Ultra Network. The Ultra Network has the following features. The first one is the multi-channel filtering enhancement, and the second one is sparsity constraint. The third feature is the prior knowledge regularization. Our proposed Ultra Network was evaluated on the homemade phantom using the typical mouse photon-counting-based CT image system. From the material decomposition results, one can see that our Ultra Network can obtain the best performance results than other competitors. At the last section, I will introduce some very interesting and explorative projects to you. At first, I would like to introduce our image reconstruction work on sparse-view reconstruction of the CBCT. To obtain the higher quality of the sparse-view CT reconstruction, we designed a dual-domain residual optimization network. We call it as JOM. Our proposed JOM reconstruction method consists of three stages: initial reconstruction, residual-based refinement, and compressed ceasing. In respect to the initial reconstruction step, there are two networks, one for projection domain and the other one for image domain. As for the second step, there is also two networks. The first one is for the residual projection domain and the other one for residual image domain. The refinement, projection, and the reconstructed images from the first and the second steps are treated as the inputs of the third compressed ceasing step. The reconstruction results for CBCT with 60 views are given. From the results, one observes that our proposed JOM obtained the best image quality than FBB Component, HDNet, DL, PIX. The extracted ROI further confirmed the advantages of our proposed JOM algorithm for reconstructing good images from stationary CT systems, such as the NanoArc system developed by the NanoX company. There are 36 distributed X-ray sources over 150 degrees for NanoArc system. Here, we designed one of the unruled deep reconstruction network named as the Sugar network for this system. From these reconstruction results, our proposed Sugar method has the ability of recovering image details, protecting image edges, as well as image features. Furthermore, these results further demonstrate that our Sugar can obtain better image quality than TV method in aspect of sparse view and limited angle reconstruction. The transformer is one of the cutting-edge techniques in deep learning. We also employed the transformer for sparse view CT reconstruction. Compared with the CNN architecture, the transformer can significantly improve image quality, including image details and features recovery. It is easy to understand that the transformer can easily capture global and local information of the reconstructed image. Till now, we have introduced our previous research work. In respect to the future work, we will evaluate and optimize the networks for clinical utilities. For that purpose, we need to improve stability, generalizability, and interpretability. We also need to distill key modules and accelerate inference, especially for core binge imaging. Finally, we will develop weakly-supervised and self-supervised methods. We need to thank our collaborators. Many thanks for your listening.